So the way we would go ahead would be for long papers, we will have 12 minutes for each presenter to present. And Lily would can take roughly around 8 to 10 minutes to present her paper. And at the end of the whole session, we can have a question and answer session or discussion. So for the first paper, we have a Mansour who would be presenting on low-level source code vulnerability detection using advanced BERT language model. Mansour, the floor is yours.
Thank you. Share my screen. Hello, everyone. My name is Mansour Alqarni. I am a full-time professor, teach cybersecurity at Fanshawe College. And also I am a PhD student at Ontario Tech University. My supervisor is Dr. Akramul Azim. So we're going to discuss this paper or this research. We're going to talk about low-level source code vulnerability detection using advanced BERT language model. So for overview, so we discuss, we know more of security and software. So we develop an application softwares, but also we make sure we detect, we do soft security testing during the process when we develop a software. So that takes a lot of time while we develop. So we execute the code, and might sometimes we will not find the vulnerability until we send the software and product or with the third party or a client and etc. We struggle to find the software. Some of the issues like vulnerability might be not vulnerable at the time when we were doing this testing or during the development. So so what do we do basically in a normal environment? We do source code vulnerability scanners. We scan the vulnerabilities, or might use traditional machine learning algorithms to help to predict the actual code, what's the code. But also we use CPP check tools to detect the vulnerabilities for only certain cases. Does not provide the entire vulnerabilities for the code. There are other softwares like Sonar Cube and AWS Cloud9. They have platforms, whereas an extension to environment for any platform, where you develop a code which we will be able to use the machine learning to help to change or give an advantage to predict the vulnerabilities. But unfortunately, some of those softwares or tools, they do look for the keywords. If you miss a keyword or a function not closing, so kind of gives you the error code error, not focused more into the vulnerability itself, into the code. So what we used in our experiment, we for the data sets, we went to GitHub and we collected a real world code for multiple softwares and applications to collect the data, where most we know GitHub, most developers, they proceed and update their softwares if they're working on a project. We collect all these resources for each of those softwares. And please, if anybody interested in the data sets or the model, send me an email and it will be available as well. So the data sets, basically, when we go to the data sets, as you see the figure number 1, the data sets, it's not balanced. And we have basically the numbers for vulnerable source code was only 7%, and non-vulnerable source code of the data sets was 93. So we wanted to expand the data sets, and we also to provide the best performance for our data sets. So we're going to discuss that in coming slides to for more explanation for the oversampling. So the data sets we collected here, we have at the table on the right where the most common vulnerability we used, where like buffer overflow, memory leaks, null pointer, and etc. So this kind table, the data sets we have, we focused more into all these 5 vulnerabilities to detect into the source code. There are other vulnerabilities, but this is the higher vulnerabilities which we focused the model and the data sets. It has more of those vulnerabilities. Also, when we run during the testing, you will see our data sets, it's not just only looking for a keyword, but actually it looks for a function. Where is the source the function coming for? It follows back to the function and check that function. It has no gap for any, for example, like looking for buffer overflow or any pointer like memory leaks. It follows back to the source of that function where it started from. If we are running through a large software or application, it reads through all those resources to find the vulnerability. When we come back through the code, this will provide us what we have for the data sets, where we found most of those vulnerabilities are the program basically detect those vulnerabilities, but we don't have enough resources to train the model to detect multiple variation of the vulnerability. So what we used for the method, we use SMART, which to detect the vulnerabilities, which is synthetic minority oversampling technique to duplicate the type of code where we have only small type of vulnerabilities. We wanted to balance the vulnerabilities. We have the exact same numbers as you see in table number 3. When we after oversampling the data, we have the balance of the information where we provide our module with the right data sets to be trained with. If we give the module to train, it's only on non-vulnerable data sets, will provide us false negative most of the time because we did not provide the right data sets to learn from. So we used SMART 2 technique where to replicate and we changed some of those data sets or languages, and those as well, it's low level. So we focused more in C, C++, and C# language, programming language, to detect those vulnerabilities. We are working in the same for more same data sets in the module, and we'll discuss that for future work where for embedded systems. So after we balanced our data sets, we used BERT, which BERT actually it's one of the state-of-art model used to transfer data from like language to another language, from English to French or French to English or another languages. So what we used, the BERT, it's been trained, and one of the state of art, the speed to transfer text from one word to another, we used the same module, but we trained the module to actually define the vulnerability in a code. So what we did with our BERT, we increased multiple layers, which we have here. What we did basically, we have multiple layer where will be all those layers are defined to for the training levels. So we have the mask, for example, where is the mask, the input for the users, like for example, programmers trying now entering their point. So the model will not interrupt their performance. We'll take that input and we'll put it as an input mask. We'll mask that, copy it into a mask, and we'll go run through the data sets, which the training, and we'll define if this actually, this code or function, it's been entered, is it causing, gonna cause a vulnerability in the future before, which actually is gonna provide the developers or the user who going to test code and etc. to find the vulnerability before they exist or before we execute the code or the software. It's gonna define where those vulnerabilities are. So we included into our module multiple dense layers where define and eliminate most of the code to make sure we go through and match this word, which is the input was in a mask, to see if this vulnerability doesn't exist or match any of the vulnerabilities we do have. If it does not, we'll drop those code, so to make it faster than just running through the code over again, and then we'll drop that code and go to another layer, which called another dense layer, to make sure to run through the same process, but it's more faster to provide us with the right result. For our results, we have achieved a higher accuracy, providing or training the BERT module into the balanced data sets. We achieved 99.30% accuracy for detecting the vulnerabilities like buffer overflow, memory leaks, non-pointer, and etc. Those vulnerabilities were only in low-level languages like for C, C#, and etc. We would be able to use the module with other languages, which currently now we are working with embedded system and a different advanced languages where be able to provide us a better performance to predict those vulnerabilities in the source code. Conclusion, we came up, we used those data sets. Again, the data sets, it's available. If you are interested to, would you like the source and the link, please reach out to the email and I would be happy to share the model BERT advanced, or we have changed, and the data sets as well, it's available on GitHub, the balanced one. That's all what I have for today. Any question? Thank you.
Thank you, Mansour. I think we will have the question and answer session after all the speakers are done with their talks. So now we'll go to the second talk where Mayar and Salma would be presenting on DTEXNet, artificial intelligence based combination scheme for DDoS attacks detection. The floor is yours, Mayar.
Yes, can you hear me?
Yeah,
okay.
We can. Yeah.
I'll start sharing my screen. Good afternoon. This is the paper presentation of DTEXNet, artificial intelligence-based combination scheme for DDoS attacks detection for the Canadian AI conference. The authors of the paper are Salma Elgendy, Omar Abdelbasit, myself, Mayar, Attawiya, Ahmed, Farag, and Paula, Branco. These are the outlines of our presentation. First, we will briefly describe the problem we are targeting. Second, we will talk about the previous related solutions. Then we will explain the architecture and idea behind our proposed solution, DTEXNet. After that, we will discuss the experimental settings we used. And then we will present the results of our solution, and finally, the conclusion. In the beginning, let's start with what is distributed denial of service attacks. DDoS attacks are one of the major cybersecurity attacks that occur when multiple systems flood the bandwidth or resources of a targeted system, preventing it from providing its services normally. The attacker infects multiple machines with malware to gain control of these machines and then uses them to perform the attacks on the targeted victim. Detection of these attacks is one of the mitigation mechanisms used. Traditional security solutions like firewalls and intrusion detection systems are unable to detect complex DDoS attacks. Using artificial intelligence-based solutions has enabled researchers to detect DDoS attacks with complex patterns. Many classical machine learning methods, such as naive Bayes, random forests, and logistic regressions, were used to detect DDoS attacks. However, classical machine learning models need extensive pre-processing, feature engineering, and prior preparations. On the other hand, deep learning doesn't require feature engineering, since it can achieve good performance in classification by directly feeding the data into the network, such as ResNet. This inspires the idea of our approach to use deep learning models and classical machine learning algorithms together to benefit from the advantages of both in DDoS attacks detection. This leads us to introduce our proposed algorithm, DTEXNet. Our approach initially compromises of tabular traffic data, 2 CNNs, and a classical classifier. We first start by preparing the data in stage 1. Then we feed the data into the CNNs and use the output to improve the original set of features in stage 2. Finally, we use the improved data set to train the classifier and achieve the required detection. We'll explain each stage in detail. As CNNs have shown great performance throughout the years, it will be an added value to use it in intrusion detection modules. However, there is only one struggle to benefit from CNNs in our application, which is we need the data to be an image format. So stage 1 is about preparing the data to train the CNN models. Our input data is in tabular CSV format. Some standard pre-processing techniques are required to prepare the input data for next steps. As you can see in the following figure, the pre-processing steps applied on one of the used data sets were dropping the missing and malformed data, dropping highly correlated features, and removing outliers and noisy records. After that, we sort the data set by labels so that every class's samples are after each other. Then we normalize the feature columns using min-max normalization. That makes the data ready for the next step, which is image conversion. As we see here, we need to create RGB images, so the data needs to be divided into chunks from the same class. For example, one of the used data sets has 66 features. So the images should be 66 samples times 66 features while preserving RGB format, which means we need 3 channels. 3 channels with 66 samples each means that we need 198 samples to form one RGB image. Finally, we map these matrices into RGB channels of an image. These images show the output of converting the pre-processed tabular data to images. An image of the benign class is shown on the left, and an image of one of the DDoS attack types is on the right. Moving on to stage 2. This stage is about training the CNNs on the formed images and benefiting from the CNN's output to improve the original tabular data set. The CNNs selected are the EfficientNet and exception networks. EfficientNet is based on the idea of enhancing the performance by carefully balancing and scaling up network depth, width, and resolution. The network developers observed that different scaling dimensions are not independent. So the architecture of EfficientNet family is developed by uniformly scaling up all 3 dimensions of a baseline network using a compound scaling method to enhance accuracy and efficiency. On the other hand, exception architecture is based entirely on depth-wise separable convolution layers. It makes a hypothesis that the mapping of cross-channel correlations and spatial correlations in a feature map of CNNs can be entirely decoupled, which allows the network to learn richer representations without having to increase the number of parameters. Now the next step is to use the classification output of both CNNs to improve the original tabular dataset. So each CNN will produce a number of probability columns corresponding to the number of classes of the used data set for each image. We will append the produced probabilities by each CNN model to the original tabular data set to make it more descriptive and informative. In black, we can see the original data set with M features, which matches the 66 features that we mentioned earlier. And in green, we can see the probabilities produced by each CNN, where each CNN produced N probability columns corresponding to the number of classes. The newly formed data set will then be used to train a classifier. Finally, stage 3 is about training the classical machine learning classifier to get the required classification results. Our selected classifier is decision tree. Selecting decision trees as our classifier is based on 3 main reasons. The first is that decision trees algorithm carries out feature selection while searching for the best fits. The second reason is that the decision tree can capture nonlinear and complex relationships without being affected by the feature scale. And finally, because the decision tree is easy to visualize and understand. We now have fully covered all stages of DTEXNet algorithm for DDoS attacks detection and classification, and it's now ready to successfully classify different unseen DDoS attacks. We'll talk in brief about our experimental settings. First, we use two different multi-class datasets to test our approach, CICD 2019 and CICIDS 2017. The following diagrams show the development of each dataset after every step in the first stage. Second, we slightly modified the selected TNNs to make them fit the requirements of the current classification problem. The convolutional layer structure of EfficientNet V0 is used unchanged. However, additional layers were added as shown in the table. All parameters of EfficientNet V0 are fine-tuned on the dataset using stochastic gradient descent optimizer and categorical cross-entropy loss function. Same happened in the exception, and its added layers are shown in this table. All experiments took place on Tesla P100 GPUs with 25 GB RAM. And finally, the metrics used to evaluate the model's performance are the precision, recall, and F1 scores. Given that the classification problem is a multi-class task, the metrics are calculated for each class. We selected these metrics as they are useful when evaluating the performance under imbalanced domains. The following figures show the results of decision tree, EfficientNet, exception, and DTEXNet on CICD 2019 dataset on the left and CICIDS 2017 dataset on the right. The results show that the performance of DTEXNet is better than using a decision tree classifier on its own or each of the CNN models on their own when applied on both datasets. This proves that DTEXNet has certainly benefited from the advantages of both models when used together. Comparing our results to the previous methods that use the same dataset, we can conclude that DTEXNet increased precision by 18%, recall by 31%, and F1 score by 26% more than the classical machine learning models used in the first course, and also increased precision by 9%, recall by 10%, and F1 score by 9% more than the CNN model used in the second course. Although our results are not directly comparable to these two previous methods, we can see that our DTEXNet has a very high performance. We conclude that DDoS attacks detection is one of the main defense mechanisms. Using both a classical machine learning model along with the CNNs allow DTEXNet to benefit from the advantages of both and achieve an improved performance. Adopting DTEXNet to handle real-time data stream is a very important future step in improving DTEXNet. Thank you for listening, and for further questions, please contact us through our email.
Thank you, Mayar, for the nice presentation. I have a couple of questions. I'll wait until the end of the session to ask you. We'll go ahead with the third presentation by Vahid. His paper is on multi-scale identity preserving image-to-image translation network for low-resolution face recognition. Vahid, the floor is yours.
Okay, thank you. Can you see my screen?
Yeah, we can.
Okay. Hello, everyone. Today I want to talk about our paper, which is about low-resolution face recognition. First, I will briefly talk about the performance of deep learning-based face recognition methods, and then I will explain on the challenges, especially low-resolution face recognition. And after that, I will explain our method and I will show you some results. Before we continue, I want to clarify about three terms. Face detection task is when we want to find all faces in an image. So we don't care about identity. We just find to find any faces in an image. Face verification is when we have two faces and we want to say whether these two faces belong to the same person or not. And face recognition is just when we have a face or image and we want to see whether it exists, that identity exists in our dataset, or that image is related to which identity in our dataset. So it is kind of n times face verification, the face recognition. Uh, Here is the benchmark of face recognition model. As you can see, there are many face recognition models which could achieve great performance on LFW or YouTube Faces dataset. And as you can see, in normal condition, face recognition models can achieve near perfect accuracy. But there are several challenges in face recognition. For example, when we have several frames of faces, um, there are different frames, and each frame contains some information about that face, and we want to find the frame with maximum information related to identity. So here the challenge is just because some of the frames are not that good, we want to find the best frame. Or another challenge is just when a part of the face is covered or occluded, or sometimes we have makeup on faces, and it makes it more challenging, especially for example for actors. Or sometimes there are different lighting conditions, and so the illumination also changes. Another challenge is just low resolution face recognition. It means that the faces are available in a very low resolution. So we don't have that much identity information in those faces. And here, most of these models, which could perform really well on normal condition, will fail and their performance will drop. Uh, in this work, we focus on low resolution face recognition, and one of the application of low resolution face recognition is just in surveillance cameras. When the faces detected there are in a very low resolution. And when we also upsample them with bicubic interpolation, and these methods, we don't have enough identity information in these phases, and we should come up with a better method. Just this slide shows how difficult this problem or this task is. If you look at these faces, this is 8 by 8 and this is 16 by 16, and even sometimes it's even hard for humans. And in this work, we want to focus to recognize the identity of these type of faces. And if we just apply bicubic interpolation, as you can see, there are not there's any information related to identity. Most of super resolution methods focus to just upsample the low resolution phase and just create or produce a high resolution image for each low resolution. But the problem in these methods is just even though they can produce a high resolution image, but most of them do not maintain identity information. So this is one of the major problem of super resolution methods. But in our task, which is low resolution face recognition, we care also about the identity. Before I explain our method, I just want to a little talk about image to image translation task. For example, suppose that we have an image of segmentation labels, and we want to create an actual image for this label. Or we have a black and white image, we want to produce the colorized version of that image. So image to image translation is just the task that we transform an input image to another image. But the important thing here is just we have the pair. For example, here we have the black and white and colorized image. Or here we have images of edges, and we want to create the texture for these images. So this task is called image-to-image translation, and we just frame super resolution problem as image-to-image translation. We had the ground truth, we just resized it to 16 by 16, and then with bicubic, we just bicubic interpolation, we upsample the image. So we use this as the input, and we want to create a high resolution pair for this image. So we just frame the problem as image-to-image translation, and here we have the bicubic image. We have an encoder-decoder architecture with the skip connections between the corresponding layers in encoder and decoder. These skip connection will help the model to localize the location of pixels more precisely due to sharing information across the layers. And this model just received the image, the bicubic version of the low resolution image, and produced a super resolved version. And since we have the high resolution image also, so we have the ground truth, we can calculate the pixel loss, the difference between the super resolved version and also the high resolution. Also, since we care also about the identity, we use a pre-trained face recognition model and extract identity features from both super resolved version and also the high resolution version. And here, based on these embeddings of feature vectors which are related to identity, we just calculate an identity loss. So then by combining these two losses, pixel loss and identity loss, we train this encoder-decoder architecture. Then we tested our model on 3 datasets. The first dataset that we used was AR dataset. This dataset has different illumination condition and facial expression, and most of the faces are in frontal view. There were 100 subjects, 50 men, 50 women, and the images are captured in 2 days. So the gallery images was taken from day 14, and the day 1 was used for probes images, and then we artificially downsampled these images to these low resolutions, and this is the example of them. And this is the performance of our model on this data set. As you can see, our model could surpass a state of the art on this data set, and on resolution higher than 30 by 32, it can achieve perfect performance. As you can see, in very low resolutions, our model perform much better than others. Another dataset which is much more challenging is LFW that we tested our model on. It contains more than 13,000 images, and 1,680 of them have 2 or more photos. And first we applied NTCNN to crop the faces, and then we remove those identities with less than 4 images, and then randomly select one image as a gallery and the rest as probe. And since it was chosen randomly, we did this setup 10 times. And these are the low resolutions that we used in this experiment. Again, as you can see, our method was able to surpass the state of the art on most of the resolutions. Another dataset that we tested our model on was SC face dataset. These faces in this dataset are captured by surveillance cameras. So this dataset is more real world, and it contains 130 identities. There are 5 different cameras with 3 various distances, and we randomly selected 50 identities for our experiments. These are the examples of these of the images in this data set. There are 2 setups defined in this data set. The first one, we chose the high resolution image as gallery, and the rest of cameras, the images from rest of the cameras are chosen as probes. Again, our model was able to surpass state of the art on most of the setup. In another setup, we chose the image from 1 meter distance as gallery, and the image faces from 2.6 meters as probe. On this protocol also, our method could surpass state of the art. And this is some visual results on AR dataset.
Vahid, sorry to interrupt you. You have 2 minutes left.
Okay. This is some visual results on AR dataset. As you can see, this is the high resolution images, and these are the low resolution that we tested our model with, and this is the bicubic. This column is the bicubic upsampling, and this is the performance of our model. And as you can see, for example, in 16 by 16, it is easily detectable, the identity of that person, which shows the superiority of our model, especially when we compare it with, for example, SR-GAN performance. Just to wrap up, we proposed an identity preserve loss function to train an encoder-decoder network for low resolution face recognition. This model is able to super resolve faces while maintaining identity. And the existence of escape connection between encoder and decoder helps the model to localize the pixels more precisely, and this increased the performance of the model. Also, our model was trained in a multi-scale setup, so it means during the training, the model was trained at different low resolutions to be more robust against different low resolutions. And thank you so much for your attention.
Thank you, Vahid. We'll have the question and answer after the final talk is over.
Okay.
Now we have Lily presenting voice cloning applied to voice disorders, a study of extreme phonetic content in speaker embeddings. Lily, you can start.
Hello. So can you hear me and see my screen?
Yeah.
Yeah. Okay. So good afternoon. I'm Lily Wadoux. I'm a second-year PhD student at Reza. And today I'm going to talk about an article called Voice Cloning Applied to Voice Disorders, a study of extreme phonetic content in speaker embeddings. And it's an article that's been written by Nelly, Barbot, Chevelu, Damien, and myself. So the idea is that some pathologies, especially organic dysphonia pathologies, can lead people to lose their voice or to have serious vocal damage. And what we would like ultimately, it would be for these people with voice cloning to type what they want to say, and the system would read what they typed with their own voice. So that would be our end goal. so to try and reproduce the patient's voice while adapting to their health constraints. So a little bit more insight on this. So speech can become very difficult for organic dysphonia patients, especially after surgery or pathology evolution. And the idea would be to record their voice once it's already very damaged, and to feed this recording to a voice cloning system. And once the voice cloning system has this recording, it will be able to, from text, output speech from this particular voice. However, there are some constraints that have to be taken into account. So because patients are not have some health constraints to come to record their voice. So there is a constraint on quality, duration, and phonetic content. The constraint on quality is due to actually, if you want to record a professional voice, you have to come to a professional recording studio. So the patient may be too tired to move, or it may be too complicated for the patient. So there is also a constraint in duration, because if you want one professional voice recorded, you may have to record for up to 1 week, which is obviously not possible for tired people. And there is a constraint on phonetic content, because patients may have a damaged voice, and so they may not be able to utter every sound. So in this work, we focus on the phonetic content constraint, and we link it a little bit with the duration constraint. So our scope of study is not yet the medical application, but rather the impact of the phonetic content on a voice cloning system. Having said that, what is voice cloning? Voice cloning is the process of producing speech that matches a target speaker voice given a textual input. For that, we use a speech synthesis device, a text-to-speech device, and the idea is to adapt it on target speaker recordings to be able to output speech from this specific speaker. How do we adapt it? In our case, we use a speaker encoder model, which is a smaller model that will extract speaker embeddings from the recording. Speaker embeddings are actually a vectorial representation of the speaker. In our case, they correspond to X vectors, because we use X vectors model. And the scope of this paper is to begin to assess the impact of the phonetic content of samples on the speaker embeddings. So for this model, we use, as I said, the X vector model, which is actually a model from speaker verification. So it's a model whose original task is to verify when it has two samples, whether they come from the same speaker or not. And from this model, we extract the embedding, so at this layer. To test the impact of phonetic content, unfortunately, we weren't able to have access to actual dysphonic voices. So instead, we had to simulate voices with impaired phonetic content. For that, we had a long, healthy voice, and we cut it into different sub-voices. So for that, we had different units depending on the phonetic content strategy we wanted to test. So we randomly extracted sentences, phones, only A phones, vowels, and monosyllabic words. And for each of these strategies, we had different durations. So we had 10 seconds, 1 minute, 10 minutes, and 1 hour. And for each of these couples strategy duration, we extracted 100 sub-voices per couple. So our experimental pipeline here is to, as I said, to extract sub-voices from a large healthy voice. And for each of these sub-voices, we pass it as an input to the speaker encoder. And we retrieve the speaker embedding. And with the speaker embeddings, we classify them and we visualize them. So we classify them with a simple naive classifier based on Euclidean distances to the centroids. And we visualize them through PCA. So the results that we have are that when we classify according to duration, the classifier has trouble to differentiate between the different durations. And when we classify with phonetic content, the classification is perfect or nearly perfect. And when we visualize it, so here you have the PCA, and the colors correspond to phonetic content strategies, and the shades are the durations. So we can see that phonetic content strategies are well separated, except for these two, which are actually, when you look at the PCA in 3 dimensions, they are well separated, but when you put it in 2 dimensions, it's not easy to see. And the idea is that the duration actually has an impact on the dispersion to the centroids. So if you have 1 hour of samples, it will actually be closer to the centroids than if you have 10 seconds, which is quite intuitive. So if we conclude, our results show an impact of the studied phonetic content strategies on the X vectors. It's a preliminary study, which is an incentive to actually investigate more on the links between phonetic content and clone voice quality and speaker similarity. We have ongoing work on this matter. And it's also an incentive to test with real dysphonic voices to get closer to the medical application. I thank you for your attention. Do you have any questions?
Thank you, Lenny. Thank you to all the presenters for the interesting talks. Now we can have our question and answer session. So if you have any questions for any of the talks to any of the presenters, please feel free to ask them now. Okay, if no one is volunteering at the moment, I have one question to Mansour. Mansour, you mentioned about the source code, right? So in GitHub,
Yes,
because
yes.
we have the version control, so does your model take into account the version control while developing the model, or like how does it work? Or does it take only the latest version? What happens if there is a repetition, only like with minor changes?
It's an basically it's an extension. The module apply is an extension to any IAD platform for coding. If any like if it's based on any of the lower level languages, the module already will apply. It's an extension will apply. But we try to, like, for example, it's going to be similar to library into the codes. So it will apply while you writing the code, will run the extension, which runs in the background of the compiler to provide the user or the developer with kind of error if there is any error. It's still under progress. We to enhance more into the module where to give a feedback which way, so just not the module just highlight that it's like the code, it's an error or it's a vulnerability. So we trying to add as many as we can to give a feedback to the programmer, not just to provide them the error, but we'll say there is, for example, this error, you could apply, give suggestions to the developer to be able to use that code instead.
Okay. Thank you. Yeah, that makes sense. Does anyone else have question for Mansour?
We have a question here from the audience. I'm not sure which presenter it's for.
Yeah.
Go ahead.
Okay, thank you. It's for the same Mansour, I think. The first paper, the author of the first paper. So I was just curious to know how did you use mode on the code, the raw code? If I understood correctly, you used mode because the data set was imbalanced. So how did you apply that initially on the data set?
So what we did with the data sets, we applied, so we used Smooth. What it does, we have the data sets, we applied it. We have to balance. So what it does, the Smooth, it takes where it's minority for the codes, which we have, which was the data set, it has higher, when we collected the data, it has higher non-vulnerable and small lower vulnerability. It was only 7% in the data sets. So we used to replicate only the 7% to give us higher oversamples, to use those little or small minority of the code to replicate more variant of the vulnerable code. So we have, so for example, you running buffer overflow. Buffer flow could comes from multiple ways, not just only one code could cause the buffer overflow. So we use that to for the data set. But the data we use Smooth to oversample the data set, and we use the data sets to train the module.
Yeah. So my question is, how did you interpolate between different code? Did you, because Smooth doesn't just add replicates, it actually interpolates the two samples. So you have two minority samples, so two vulnerable codes. You actually interpolate those codes, so you actually mix the lines of the two. How do you do that?
Yeah, so we had to run a random for those codes to take the codes to sample those codes. Yes. So we did like at the beginning of the process, which we used it in our previous research paper. So in this paper we used the same scenario, but we have the background where we did selected multiple the codes to the Smooth to use it.
Okay.
So so we had to basically use a static way to train it, to select the codes.
And then after having the code, sorry, can I just ask another question? After having the code balanced, then you split it into train, test, and validation. Is that correct?
Yes.
Okay, and then you evaluate the performance on the balanced, and that's why you use accuracy?
No, well, what we did actually, let me go back to open my paper actually.
Sorry.
Here. Let me go back to the slides, because basically I put at least some basic slides, because 12 minutes, I don't thought it's not fair to put all the data. When you see the data sets, so training, split the data to so we got the training. What's the training, which you saw on the table? We have training, validation, and the testing, and the accuracy came out when after the training we validate this information after it's been trained. We test all the data, so we put some examples. We use some of those raw code we used from the softwares, and we got the test, and that's what's the testing. We have the accuracy based on that. It's still not accurate when it came to using different languages, but basically it's only for the lower languages, and that's where we split the data to enhance. So as well, when we use the bert for the module training, we used random to select a percentage to train the module, not to train it at once. As earlier, we for I believe Nicholas for his note where he discussed we need the best solution to design or to train the module, not to train it to provide the entire data set, which exactly we used 15% at a time to train the module.
Okay, okay. Thank you so much. Thank you.
Thank you.
Good questions.
Good questions. Any other questions to any of the other presenters?
Yeah, I have a question. And this question is for the last presenter, Lily Wadoux, right? It's just a question of curiosity. You remember the famous physician, Stephen Hawking?
Yeah.
Yeah? Do you think your system would solve a problem like the one he had? So the challenge here, let me finish the question. The challenge here is that in the case of Stephen Hawking, you cannot clone his voice because that was an extreme case, right? There was almost no voice. So what do you do in that case?
So the ultimate goal would be to be able to clone such voices. But we are really at the beginning of it. We are just doing the preliminary study to see if very altered voice has an impact or not. And the next steps would be to try and come up with solutions. First on basically altered voice, but later on very, very altered voice. And we hope for it to be possible, but we are not there yet.
Okay, that's fine. It's fair. That's fair. Yeah. Okay. Thank you.
Welcome. Thank you for your question.
It's a really an interesting application. I really like it.
Thank you.
Any other question from anyone? We have 4 minutes left. Okay, if not, I have a question to Mayar. Mayar, you presented on the denial of service attack, right? So I was just curious whether, do you want to approach on the unsupervised side of things? Because when such attacks happen in real time, you might not have a specific behavior or a specific supervised sort of model that can actually help in flagging the events or finding the events. So that was one question. And the second question, probably I might have missed it. I wasn't sure whether why you are converting the tabular data into the image format. So these are my 2 questions.
Okay, for the first question, this is actually one of the steps that we will be doing in our future work, because our model now is working only on offline data. And to make it work for data streams and online data, what you asked will be certainly one of the major steps we need to improve our model for. And I didn't catch your second question.
The second question was why are you converting the tabular data into image format? Probably I missed that part in your presentation.
Yeah, sure. Because our approach, DTEXNet, it first, yeah, I can share my screen and just show you the architecture very quickly. Yeah, here. So first, our algorithm consists of 2 CNNs and then 1 decision tree. So our input data is initially in CSV format, and we have to feed it into the CNNs. So to do that, we have to convert it first into images to be able to train the CNNs on the data. So this is where we do it here in the tabular data to image conversion. To feed it to the CNNs, and then we append the result of the CNNs to the original tabular data set and use this to train the decision tree.
Okay. Okay. Yeah. Thank you.
Thank you.
Any more questions? We are almost at time, and thank you again to all the presenters. And if you have any other questions, we can continue the discussion on Gather Town. And good to see you, everyone. Thank you.
Thank you. Bye.
Bye.
Cool. So on the AI track, we'll be taking a 15-minute coffee break at this point, and we'll be resuming at 3:45 for our next session on natural language processing. So for those of us here in person, feel free to step out and grab some coffee or something to eat, and we'll be back in 15 minutes. Thanks, everyone.
Hi, everyone. I would just like to check if all our presenters are here. Is somebody presenting quantifying French document complexity?
Yeah, Ahmed there.
Hi, Vincent. Is somebody presenting sample efficiency? The name of the paper is Sample Efficiency and Deep Reinforcement Learning Based Recommender Systems with Imitation Learning. Is somebody going to present that paper? Okay, so we might have one presenter missing. Is somebody here presenting a working model for textual membership query synthesis?
Yeah, I'm Sir.
Hi, Frédéric.
Hi.
Is somebody presenting computational models of linguistic alignment? This is a paper by Duncan Cleland and yeah.
Yes, I'm doing that. Sorry.
Oh, hi, Duncan.
Hi.
Is somebody presenting on the influence of annotation quality? This is a paper by Fanny Rancourt, Diego Mopome, and Marie-Jean Meur.
Hi, we have a presenter here.
Hi. And finally, is somebody presenting data set augmentation using back translation and so forth? The paper is by Marc Queudot, Louis Marceau, Raouf Monsef Belbahar, Eric Charton, Marie-Jean Meur. Is it the same presenter, perhaps, as the previous short paper? Okay, so we might have an issue with the last one. Okay, let me see. Okay, so it's 3:44. We'll be starting shortly. I see a Marc in the audience. Is that Marc Tessier?
No. Sorry.
Well, welcome anyway.
Thanks.
Well, I hope our second and last presenters will show up eventually. I'd like to welcome everybody to this session on natural language processing. My name is Gabriel. I'm a research officer at the National Research Council. First of all, I'd like to apologize if I sound phlegmy or if you see me blow my nose because I'm a bit sick at the moment. I see that Behrouz has joined the session. Behrouz, are you the one who will be presenting the second paper?
Yes, that's me. Yes, okay. I'm going to present
the
second paper.
And welcome.
Thank you.
So I was just finishing the introduction. So today we have 4 long talks and 2 short talks. So I'm going to ask everybody to try to respect your time limits. I would just like to remind everybody that the 4 first talks are 12 minutes each, and the 2 last talks will be 8 minutes each. It's important that we stick to this time because we have a pretty packed program today. I will, if you are looking at the Zoom, I will, oh, is that reversed? Anyway, I will put up this sign. Maybe I can flip it up. Oh, that works. Okay. I will put up this sign when you have 1 minute left, and I will interrupt you if you go over. Is there anything else I need to go over? Oh, yes. For the questions, the organizers have asked that the question and answer period will be at the very end of the session and not after each individual talk. So if you have questions for the speakers, I would ask that you note them so that you remember them at the end of the session. And with that, I think that we can get started. Let me just get my program. So our first talk is entitled Quantifying French Document Complexity. The authors of the paper are Vincent Primpier, I'm guessing, David Beauchemin, and Richard Coury. And I think Vincent is here. Vincent, with that, I'll let you get started.
Just a moment before, your sign were on the right way the first time. So we're not with us. Yeah, that works.
Okay, thank you.
Yeah, okay. So I will share my screen. Okay, up. Is that okay? Up.
Yes.
Okay, that's great. Okay, perfect.
Yes.
So hi, I'm Vincent Primpier, as you said. I'm glad to be presenting our work. So I've worked with Richard Coury, who is an associate professor at Université Laval, and David Beauchemin, a PhD candidate in Université Laval. So we'll see today how we manage to quantify French document complexity and moreover generic complexity. Why I say that is because all of the application today on the side of the natural language processing is very specific to an application domain. The example I take here is à mesure, which is an application that assess on the complexity on administration documents. So it's a very specific domain. Moreover, most of the work are done in English, so when you're trying to assess on a French document, it's really hard. So the principal goal of our work were to build an application made for French and moreover on a generic complexity. We'll see how we did it in 3 points. First of all, we'll see how the complexity expresses itself and how we can measure it. It's not easy all the time. After that, we'll apply some of machine learning models. We will see a little bit how they perform and more succinct why they perform. And finally, we'll make a little insight of French complexity and what the model are telling us of this complexity. So going back to complexity, the main problem we have is there is no generic definition on complexity, so we need to approximate. What we made is we identified 8 main type of documents, from the children's stories to laws, that represent intuitive complexity levels. That allows us to discretize our problem from 0, the easiest one, the children's stories, to 7, the hardest one with the law. Just a little word on the corpus. We built our own corpus because there were none where we're trying to find one. There is 118 texts, and we select them for representativity. There is a great explanation of how we made it and the choices we've made in the article, so you can see more precisely if you want. Now we've seen a little bit of expression of the complexity. We can see how we can measure it. We identified metrics. We made a selection of metrics that measure aspects of the text. In the first part, I will introduce you in the left-hand side with the complexity views. The idea behind these views is that we're trying to measure aspect of complexity, aspect that directly causes complexity. For a simple example is, I don't know, mean length of sentences. It's really intuitive and really logic to say that the longer the sentences is, the harder the text is. So this is the goals of these views. We have 4 views in the complexity aspects: the syntactic complexity, the lexical diversity, the readability, and the vocabulary complexity. In the second part, on the right-hand side, we thought that adding a characterization view will help the models to perform better. In fact, we made an adaptation of the Bieber tagger for French that really measure aspect, not only complexity aspect, but aspect on the text. A simple example is the mean number of present verb, for example, on a text. This allows our models to build their own metrics, like to combine some aspects of text to make kind of new metrics, their very own metrics, metrics that we may not think of when we were building our complexity views. So these 5 views made for us 63 metrics. 63 metrics. So we have our corpus, we have our measurements and our metrics. So now the models. We choose 5 models, like a Condell-and-Moll formula, which is more a formula than a models, a decision tree, a logistic regression, a multinomial naive Bayes, and a random forest. We use the Condell-and-Moll formula as a baseline because it's the last known very generic work on complexity. A measure, like I talked before, is not very relevant to compare with because it's really specific to an application domain. We took 2 metrics to rank our models, RMSE and accuracy. Accuracy, which is there, like a very standard accuracy to measure how precise our classification work. And we introduced the mean error metric, even though this is not a regression problem, because we thought that if I came to say that this text is extremely difficult, and you came to see me and you say I do not agree, it's very difficult, we can argue, and I may say, okay, I see you what you're saying. It is very, very difficult, so we can get a middle ground. And this idea is that when the model classify a text, we will look at how far it is from what we said about this. So we thought it will be an interesting measure to rank our models. What we can see in this slide is the separation on the table. In the first 2 rows, red in the red color, we have models that only use a fraction of the metrics. They were trying to identify a discriminator or some discriminators to separate the class, but the problem is way too complex to classify to classify text only with few metrics. In the green section, we have the chosen ones, the ones that used all of the metrics. Even the highly correlated ones, so they used every metrics. We can see here that the random forest performed the best with the RMSE of 0.21 and an accuracy of 0.92. Remember, I said that we've approximate the generic complexity. So to test for our validation set, we took completely unknown type of documents from our models. So we make a little bit like our corpus. We took type of documents. These ones were completely unknown for our models. We gave them intuitive complexity levels in the expected column, and we gave this set to our models, and we computed the mean predicted level for each class for each model. And finally, we computed a correlation between the expected levels and the predicted levels, the mean predicted levels, in fact. And we can see that it generalized well, even though we approximated the application. We can see that the best model here is the logistic regression. The naive Bayes and the random forest may be overfitting a bit. So yeah, for the logistic regression, great generalization. Now that we've seen a bit like how they perform and how they perform, we can look a little bit inside of the logistic regression, and we can identify the coefficient for each metric. this table make like a compilation of some of the metrics with high coefficients in positive coefficient and negative coefficient. It's one for each class. The first thing I would like to point out is that really simple metric, such as the mean world length, is used by it's used by the logistic regression. And moreover, we can see that it uses it very intuitively, like it's very logical. We have, for the children's stories, for example, the mean word length in a negative coefficient. It means that the shorter the words are, the easier the text is. We can see the same thing in the news articles. And in the positive coefficient column, on the dictation and insurance document, it's highly positive. So the longer the word is, the harder the text is. And this kind of combination of metrics can confirm, in fact, our confidence in the prediction and can like reassure us when it made prediction on really new text. The second point I would like to point out is, as I said before, they used all of the metrics, even very close to one. We have here the MTLD and the mean sequential TTR, which are two adaptations of the TTR. And we can see that they used to express similar characteristics, but the slightest variation can discriminate two closed level of complexity. So yes, the adaptation capture information that are useful for classification. Of course, this part is extremely detailed in the article, so if you want to go further, I'll invite you to read it. It's extremely interesting. A little conclusion to this. It's our main contributions. We made a Python library available on GitHub, text complexity computer, that integrate our models and the metric computation, etc. The whole pipeline. The French-Canadian complexity level corpus, as I talked a bit earlier, and a methodology that can be reused to other languages and to make similar application. So that's ring the bell. I will thank Beneva and the NSERC to the project, because without them there will be no project. Thanks to the Canadian AI that can allows us to present. And I will make a special thanks to Richard for the opportunity. Yeah, that were really interesting and great.
Thank you, Vincent. Very interesting talk. Please, people, applaud virtually if you want. We're going to move on straight ahead to the next talk. I believe it's Behrouz who will be presenting this paper. Let me go back to the program. The paper is entitled Sample Efficiency in Deep Reinforcement Learning-Based Recommender Systems with Imitation Learning. So Behrouz, please take it away. You have 12 minutes.
Yes, please. It seems that my camera has quit on me, so I will try to make it work. And let me share my screen with you first. Just a second. Share the screen. Okay, I hope that you can see my screen, and let me bring it up. Okay, so I hope that everything is fine and you can hear me. It seems that my camera is not going to work. Just let me try one more time. Anyway, so let's talk about the topic. Sorry about the problem. And also there is some construction in my building, and you may hear some noise in between the talk. I apologize for that in advance. Okay, so the presentation is about the improving sample efficiency in reinforcement learning. Okay, we all know that reinforcement learning in general has the problem with sample efficiency, and we want to improve that using some kind of imitation learning using algorithms that are used usually for recommendation systems. Okay, so the next is the agenda for my talk, and the agenda is basically I'll first talk about what is the recommendation systems, what is the reinforcement learning in very general. I know that everyone is expert in this field, so just a brief intro to recommendation systems. Basically, we all know that there are two types of recommendation systems that usually we compare the items with and recommend a new item or compare similar users. So those are the two type of recommendation systems available, and classical algorithms for that are the collaborative filtering and content-based filtering. The reinforcement learning actually is a little bit more problematic in this type of application. Basically, we want to build some applications that can recommend some, for example, text or information to the original project was to recommend to some patients based on the diagnosis that they receive from the physician. So for the recommendation systems in that way, using reinforcement learning usually doesn't work properly because of the problem of the sparsity of the database that we have, and the sample size should be quite huge in order to get some meaningful how to say evaluation in order to base the strategy on. Of course, we all know that reinforcement learning usually works for the type of control problems. For example, when you bring somehow the point that you want to reach to close to where you want to do what you want to do, and then use reinforcement learning to improve on that. But our problem is not that type. It's quite different. And we found out that the idea of imitation learning, especially when we are doing the exploration part of the reinforcement learning, is quite or can be quite helpful. In imitation learning, basically, we try to imitate an expert. Okay, the expert can be either present or not present, and basically we have a kind of behavior of the expert available in the form of, for example, a state and the actions, sequence of states and actions, and the agent or the program wants to mimic that. Okay, so the motivation for this research is, as I said earlier, okay, the reinforcement learning, it takes into account the dynamic user behavior. It can handle the problem with the cold start users and doesn't need user rating. So these are good things with the reinforcement learning that we want to use in this project. But then the catch is that, as I said, the sample inefficiency is the main problem that we have. So when the environment is complex, basically means that we have a huge number of states of the environment, then selecting the right state and then the right action based on the current state usually is difficult, unless we have lots of information available at hand. So the solution that we provide is the combination of reinforcement learning and imitation learning. So we call it the IR2S. And actually, there is a GitHub for this also available, and we will share. We have shared the code there. But anyway, so we want to see that whether imitation learning can work well with the reinforcement learning or not as the first step. Okay, so for the reinforcement learning, we can use different algorithms that are there. We use just the deep Q network or DQN as that part. And then for imitation learning, we use two strategies. One is the item-based, and then the other is user-based neighborhood collaborative filtering. The next slide basically shows the pictorial view of the system that we have. Okay, so on the left side is the user, and the program wants to recommend something to this person. Okay, usually if we use just the DQN is composed of the algorithm is composed of two parts: the exploration and exploitation part, and we want to replace the exploration part with the imitation learning. Why it is good? Because it will help us reach the conclusion faster, basically. We can say it that way. Okay, so we want to see that whether this works or not. Basically, if we remove the exploration part and add the imitation learning, does it work well or not? That's the first step that we want to perform. So for this, we set up an experiment. We use the movie lens data set in two versions, 100K and 1 million records, and the number of users and number of items and ratings are given in the table that is in this slide. And for the baseline that we want to compare or add the imitation learning on top of it, we use two algorithms, DQN and Year's algorithm. So the metrics for evaluation, we have to define basically or use some metrics to see that whether it works or not. We use the HR and NDCG metrics. The details are in the paper, and I just want to show the results of this experimentation that we have. In these two figures, on the left is for the first data set, on the right side is for the second data set. The horizontal line is the number of items. We are using the item-based collaborative filtering as the imitation part of the work. So then horizontal line is the number of items, and vertical line is the metrics. Okay, the higher the metrics is better. And we will see that for the two metrics that we have, measured. It seems that 10 items shows the best results for both metrics, the red line and the blue line. And it is consistent between the two data sets. So basically, we can conclude here that we can use the imitation learning as a replacement for the exploration, and for up to 10 items, the best results can be achieved by up to 10 items that has been recommended. In the next, we use the user-based approach or user-based collaborative filtering. And again, we see that for example, for the smaller data sets, the movie lens 100K, again, 10 items is the sweet spot here, and the higher value for the metrics are recorded for that sweet spot. So it seems that good, but for the larger data set, this was a little bit controversial results that we got. For the larger data set, the highest point that we get on the graph is for one person, because it is user-based, one person, and we get the highest, ranking. And this is a little bit controversial. So basically, we can conclude that the user-based approach may not be working consistently with the setting that we have or with the data sets that we have, but the item-based approach works well. Okay, to what extent it works well, I have shown you in this slide. In the two bars that are purple and red are the baselines, basically the DQN and DEERS algorithms. And then the three green and orange and blue lines are the extension or convert using the imitation learning in our extension to those two baselines. And we will see that in both cases, both for the a smaller data set and larger data set, we get some percentage between 70 to 400% higher, I mean, improvement on average. Basically, it means that yes, the using imitation learning in the sense that we have used works well with the recommendation with the reinforcement learning, but there is a catch that depending on the algorithm that we use, maybe the results can vary. So I can conclude that combinations of reinforcement learning and imitation learning can, to some extent, address the sample efficiency. And we have to work more on this with other data sets and maybe with larger data sets and so on. And we have also worked on a way of I mean, overcoming the limitations that we had with the user-based approach by giving a kind of chance to the algorithm to select between the demonstration that is part of the imitation learning and exploration that is part of the original, for example, algorithm for reinforcement learning. And in this way, I think that we can fine-tune our data set to or data sets to the algorithm and basically use imitation learning in an efficient way for multiple resources. Okay, that's the end of my talk. I hope that I haven't passed my time. If you have any questions and comments, please email me or I should mention that the work was originally by one of my students, Mehdi, but he has convocation today. So he asked me to present it on behalf of him. Thank you.
Thank you very much, Behruz. Our next talk, let me see if I can launch my video here. Oh, now my video is not working. Oh, there we go. Okay. Our next talk is by Frédéric Piedboeuf et Philippe Langlais. And the name of the talk is a working model for textual membership query synthesis. Again, you have 12 minutes, so take it away, Frédéric.
Can you see my screen fine?
Yes, beautiful.
Perfect. So yeah, the paper is called A Working Model for Textual Membership Query Synthesis. And the problem we're looking at is the problem of data collection, which is often a long, costly, and inefficient process. So of course, the question is, how can we attain a good performance with less undated data? And one of the techniques that does that is active learning. And more specifically, we're going to look at membership query synthesis for textual data, and membership query synthesis being a subset of active learning. So for those who don't know, active learning exists in contrast with passive learning, which is the classic way of collecting data set where you collect unlabeled data, you label it, and you just pass it to the classifier. And active learning, we add an interaction between the classifier and the labeling process. So I have an example here, which is a confidence strategy. So at each iteration, we're going to come and select the unlabeled sentence, which is the closest to the decision boundary, under the assumption that this is the most informative one. And membership query synthesis, it's a variation of the idea where we're going to select the point in the classification space, which is the most informative, and we're going to generate a new sentence from it, label this new sentence, and add it to the dataset. So in membership query synthesis, we create a dataset of generated sentences that we hope are highly informative. So theoretically, membership query synthesis is very efficient because we can really ask the class at any point in the space. But the main drawback is that, well, most classification space are not dense, right? So the data lives in a manifold, so we can't just ask the class of any point because most points are not going to correspond to a real sentence. So what is done in practice and what we do here is use a latent space. So we're going to use a variational autoencoder to find out that latent space. And the latent space is dense and continuous. So we're going to use this space to select which points to generate, transform into sentence and label instead of the classification space. So MQS is fairly understudied. There's maybe like 3 or 4 papers that have looked at it practically. It's just been studied a lot from a theoretical point of view to show that it's a very efficient way of training a classifier, but practically it's not studied a lot. So what we wanted to do today is simply to test if it can work on a real data set, as well as start testing some strategies that could work better. And one point to notice is that since we use a variational autoencoder, and since variational autoencoder is not as efficient as human to create sentences, we don't really expect MQS at this point to beat active or passive learning, but we simply wanted to start assessing the capability of MQS for creating data sets. So here we have the general flow of MQS. And of course, we have at first a data set, which is composed of unlabeled data, as well as a few already labeled data randomly selected, which is called the seed. And this seed is used for the first few iterations. So at the beginning, we already need some information as to which point we want to generate. And then in a classic MQS loop, we're going to first train the generator and the classifier. So the generator on all the data and the classifier on the seed. And then we're going to encode all the data in the latent space. We're going to select which points we want to label with some strategy. We're going to decode it into a sentence, label it, and add it to the dataset. And we do this until we reach the labeling budget, at which point we stop, we train or fine-tune the classifier one last time, and this is our final result. So the core of MQS is, of course, the interaction between the generator and the selector. So this is where we'll test some strategies, and we'll test 5 different strategies. So first of all, of course, we'll test the variational autoencoder with the simple random selection, which is kind of a baseline. And then we'll test something that is called a decision boundary selection, which has been tested on toy dataset before. And the idea is simply to encode the data in the latent space to find out the decision boundary, as we can see here, and then to sample from each side of it going alongside the decision boundary, under the assumption, once again, that they're going to be very informative sentences. Other than that, we're going to test 2 different generators, so a conditional VAE and a semi-supervised VAE. And so both are trained to generate sentences conditioned on the class, but the CVE is trained to generate condition directly on the class, while the semi-supervised VAE is trained to generate condition on the distribution of probability. So the CVAE has the disadvantage that it can only be trained on labeled data, which is a resource that we don't have much of in this context. So the semi-supervised VAE is kind of the solution to that. So we train to generate based on the distribution of probability, and this distribution is decided by the classifier. So it's the output of the classifier. So we add with the semi-supervised VAE a link between the classifier and the generator, and this will also allow us to have a strategy which we call confidence, and which we will directly ask the semi-supervised VAE to generate sentences for which the classifier is uncertain. So the 2 strategies that we hope will work better is obviously the decision boundary selection, as well as the confidence selection with the semi-supervised VAE, and the others are kind of baselines. Other than that, we'll test with 2 real baselines as well as 2 upper bounds. So for 2 baselines, we'll have using only the seed to train the classifier, as well as using a simple autoencoder with random selection. So instead of a variational autoencoder, just a regular autoencoder, which will be a baseline. And our 2 upper bound will be passive learning and active learning confidence. And as I said, they're upper bounds because since we compare a data set of generated sentences versus a data set of genuine sentences written by human, we don't really expect the generated sentences to be better. And finally, some more technical details. So for the dataset, we'll use SST2, which is a dataset of movie reviews classification. We're going to test 3 different sizes of seeds and a total budget of 500, which mean we'll generate until we reach 500 total sentences, at which point we'll stop, fine-tune the classifier one last time, and then check the performance. For the classifier, we'll use BERT. And for the labeler, theoretically, it should be a human, but it's very expensive to have a human label all of these examples. So we'll take inspiration from another paper and we'll use a BERT that is fine-tuned on the train and the test to simulate the human component. And in the paper, we go into some more analysis of the difference that this makes versus having a human annotator versus a BERT annotator. But yeah, so this is a way to kind of have a proxy on which we can do fast experiments. And so here we have our results. So on top, we have the seed size. Here we have the strategies. And then each entry is the average over 6 runs, as well as the standard deviation. So a couple of things to notice. First of all, our 2 baselines don't really work, which is not surprising. And our 2, the passive and active learning strategies work fairly well, which is also not surprising. For MQS strategies, we have the VA random as well as the 2 semi-supervised VA, which works pretty well. And in fact, we found out that they work as well as passive and active learning, which is really surprising. So we did not expect that. And once again, in the paper, we go into some more analysis as to why that could be the case, since as you'll see in the next slide, the sentences are clearly not at human level. But then we have also the VA decision boundary and the CVA, which don't work. So we expected the decision boundary to work well, but it doesn't. And finally, we have the semi-supervised VA confidence, which we also expected to be better than the other strategies, but it works well, but it doesn't beat the other MQS strategies, which is kind of a disappointment also. And why don't some of these strategies work? So for the decision boundary strategy with the VA, the idea was to find the decision boundary in the latent space, but we found out that when the data becomes sufficiently complex, the VA is not able to separate classes in the latent space. So if the data is simple, for example, MNIST or a toy dataset, then the classes will be separated in the latent space with no problem. But if the data becomes complex, for example, SST2, what we consider important characteristic of the data will not necessarily be considered important characteristic for the VAE. And if the classes are not separated, finding the decision boundary will not work and the strategy will just not work. Then for the CVAE, as I said, we can only train it on labeled data, which is the seed. So there's very few data to train it on. And as we can see here, it doesn't generate good sentences. So it makes sense that it doesn't work well. And finally, for the semi-supervised VAE, well, it turns out that BERT is very overconfident in its predictions, which means that the semi-supervised VAE never see examples or rarely sees examples for which BERT is not confident. And so when we ask it to generate these examples for which BERT is not confident, it just doesn't know what to generate. So it generates either confident positive or confident negative examples, which is why it doesn't work better. And so here we have some example of sentences generated by the autoencoder as well as the 3 generative models. And we can see the autoencoder and the CVAE generate pretty crappy sentences, which is what we expected. And then we can see the variational autoencoder and the semi-supervised VAE generate pretty good sentences, so not human level. We can clearly see that these are generated by computers, but they're not that far either. We can see that these are positive movie reviews, which is the goal, and clearly they're informative enough for BERT to fine-tune correctly on. So in conclusion, we've shown in this paper that MQS can work efficiently on a real task. So this is not something that had been done before. So obviously, as I said, there's maybe like 3 or 4 papers that have looked at MQS practically. So there's a lot of improvements that are possible. We simply tested some things here, and we've used pretty basic versions of the algorithms. So I've written some ideas here. So for example, we could use a disentangled VAE with the decision boundary strategy, which would probably work better. We could try pre-train large generative models such as GPT-2 or 3 since a random selection seems to work well anyway, so why not try these GPT models? We could use calibration of BERT for the semi-supervised VE. So there was a talk this morning, I believe, on calibration. So this is an idea that should probably improve the model significantly. We could try interaction of active learning and MQS. So there's a lot of things to do. And we hope that this paper will kind of serve as a baseline for the future of MQS, and now that we've shown that it can actually work. So thank you for your attention.
Thank you, Frédéric. Again, you were on time, so I appreciate that. I'd like to mention that the paper that he was talking about, I believe the title was Adaptive Calibration, or Adaptive Confidence Calibration, something like that. I thought that was an interesting talk as well. Okay, without any further interruptions on my behalf, excuse me. Let's move on to the fourth talk. The fourth talk is entitled Computational Models of Linguistic Alignment for Clustering Group Participants and Predicting Task Outcomes. I believe Duncan will be presenting this paper, and the authors are Duncan Cleland and Gabriel Murray. So Duncan, please.
Perfect, thank you very much. All right, can everybody see my screen?
Yeah.
Okay, excellent. Hello everybody, and thank you very much for coming today. I'm going to be presenting the research Dr. Murray and I did on computational models of linguistic alignment. Now, a good first question you might ask yourself is, what is linguistic alignment? And very basically, it is how similar two individuals are in their speech to each other. Another good question is, why does this matter? The reason is previous research has demonstrated that linguistic alignment is related to things like performance in a group, how likable and intelligent the other people that you're interacting with perceive you or you perceive them to be, and has been related in several cases to things like group dynamics and the power held by individuals in an interaction. So the research on linguistic alignment has progressed to the point where multiple measures are now available. And so we had some questions about a few things about the various measures. So our key kind of questions were, how do short and long-term linguistic alignment measures relate to each other? Or short or long-term linguistic alignment features more effective when you're trying to predict the performance and satisfaction of participants in a group? And how does the proportion of each conversation analyzed affect the performance of prediction models? Or in other words, what is the ideal amount of conversational context we need to give a model to achieve the highest performance? We did our research on two publicly available human-human interaction data sets, the Group Affect and Performance Corpus and the Universal Group Interaction Corpus. Both of these are survival task scenario data sets where individuals come to the experiment and are given a list of 15 items that they have to rank in their importance to surviving a hypothetical disaster scenario. For the GAP corpus, individuals are survivors of a winter plane crash, and in the UGI corpus, individuals are astronauts who have experienced the breakdown of their lunar exploration vehicle. Now, if you're thinking one of those things sounds a little more complicated than the other one, you would be absolutely right. The performance of participants in the lunar survival task is on average about 20 points lower, and the satisfaction of individuals within that task is similarly much lower when compared to the GAP corpus. So those are the data sets we were looking at. The two measures that we chose to investigate, we have one short and one long-term alignment measure. Our long-term alignment measure is entrainment. Entrainment is very simply the similarity in verbal behavior or word use of at least two individuals. And we're interested in convergence, which is the change in entrainment over time, or in other words, how people become more similar as the conversation goes on. Now, like anything where you're trying to measure changes over time, we need a before and an after to compare. So what we did was we took the first and last X percentage of a transcript, ranging anywhere between 5% to 50% for a conversational frame, which encompasses between 10% and 100% of the actual conversational transcript itself. The features that we used to examine the long-term entrainment were function words and psycholinguistic features. Function words include such things as adverbs, pronouns, articles, etc. And psycholinguistic features are more of a meta feature that covers things like the age of acquisition for words, its familiarity in common usage, and how concrete or abstract it is. Our short-term alignment measure is coordination. And unlike our long-term measure, coordination is the propensity of an object or individual to alter its behavior based on the behavior of another object or individual. Or in plain language, if I say something to somebody, coordination is their propensity to use the same language when replying directly to me. So it works on more of a call and response type of feature. Because of the way it's calculated, coordination uses the full conversational transcript in each case. So it uses equivalent data to the 50% frames. When calculating coordination, we also used function words, and they were an identical set of categories to the long-term alignment function words. Now that we've got our data set and our measures, the next thing to do was to calculate convergence and coordination for all of our participants. For convergence, we extract our two portions of the conversation. And then for each feature in each of the frames, we look at everything that an individual participant said. We figure out what proportion of that was our target feature for each frame for each participant. And then we calculate the convergence score for each participant with each other participant, generating a pairwise score for all possible combinations of two within a group. And then we average that pairwise score to get an average convergence for each speaker for each feature. For coordination, it's a little bit simpler because we're just looking at call and response. So we simply calculate the pairwise convergence or coordination between each member of the group and then aggregate it to get an average coordination score for each speaker for each feature. Once we did all of that, we could start answering some of the questions that we had, like, is there a difference between short and long-term linguistic alignment measures? And if there was, because we use function word categories for both of them, on the 50% frame where they're using the same data, we would expect to see a high correlation for between, say, adverbs for coordination and adverbs for convergence. However, in all cases, we found that there is almost no coordination or almost no correlation. So which demonstrates short and long-term linguistic alignment measures are capturing different complementary data. In order to look at in more detail and examine kind of the properties of, to examine the properties of the various convergences, we performed clustering. In both cases, for both corpora, we found that there was a high performing cluster who were individuals that had higher satisfaction scores and higher performance scores. And our clustering, we're primarily interested in three kinds of differences. The differences between clusters in the same frame and the same corpora, the differences between clusters within the same corpora but in different frames, and the differences of clusters between different frame or in the same frame and different corpora. And what we found in the gap corpus is participants who had a higher convergence on personal and object pronoun usage and interrogative pronoun usage were the people who did better. So people who referred to their own work and asked questions of each other in an equitable way outperformed groups that didn't have that. Now, in the UGI corpus, at the 5% frame, we find that interrogative pronoun usage is also a feature of the high-performing cluster. But interestingly, at the 50% frame, this undergoes an inversion, where the people who asked a significantly different number of questions tended to perform much better than the other members of their group. Because this is just two groups ranking a list of 15 items, you wouldn't expect to see such a great diversity in asking more or less questions being a divisive feature. So we kind of turn to the success of or the difficulty of the task itself. The UGI corpus uses the lunar survival task, which is a lot more complicated and benefits a lot more from specialized knowledge about space environs, engineering, and physics. So we suspect that inversion of interrogative pronoun usage comes from people who are asking far fewer questions because they have a great deal of knowledge, or other group members identifying the group member who has a great deal of knowledge and asking them significantly more questions. So those were some of the interesting features we found. There are many, and I don't have time to talk about all of them, but so that was what we found with clustering. Our next question, which was whether or not, or what the ideal amount of conversational context was in terms of frame size to get the best prediction performance. We actually found, when we used gradient boosted and random forest models for both the GAP and the UGI corpus, and for both performance and satisfaction, the 5%, the models using just the 5% frame, so a very low amount of conversational context, outperformed everything else. Which was somewhat surprising, but is consistent with a lot of other research into conversational context for meeting data. Our third question that we were trying to answer, which was, are short-term or long-term linguistic alignment measures better when you're attempting to predict performance and satisfaction? We found that when you're looking at trying to predict performance, long-term measures or combined measures, so how similar people become by the end of the conversation, is a stronger predictor of performance. And for satisfaction, the coordination or the immediate call and response has a higher predictor of whether or not people found the interaction to be enjoyable. In conclusion, the three kind of key things that we found were short and long-term linguistic alignment measures do seem to be capturing different sorts of information. Our feature group, when we're examining feature groups to see whether short or long-term measures are better for predicting satisfaction, short-term measures predict satisfaction better, long-term measures predict performance better. And regardless of all of that, the highest performance that was achieved by the prediction models was with the smallest amount of conversational data we tested, just 5%. And yes, that's what we found. Thank you very much for your time. And we'll be around to take questions later.
Thank you, Duncan. I expect we won't have much time for questions in this session because it ends at 5 and we have 2 8-minute talks. But I'm going to mention to everybody that we have a GatherTown meeting, or a meeting place in GatherTown where we can discuss with the authors after the session. I apologize for my phone going off. I will turn it off. Okay. Now, we have 2 short talks to finish this session. The first is titled "On the Influence of Annotation Quality in Suicidal Risk Assessment from Text." The authors are Fanny Rancourt, Diego Mopome, and Marie-Jean Meurs. Is it Fanny or Marie-Jean that will be presenting this paper?
It's me, Fanny.
Fanny, then go ahead, please.
Yeah, just
yeah, we can see
put
it
in slideshow. and start my timer. So hi everyone, today we'll talk about annotation quality in suicidal risk assessment from text. This is a joint work with Diego Mobome and Mahjong. To assess annotation quality, we mostly use error analysis and inference functions. In general, mental health detection class are extremely important because mental health disorders are extremely widespread in the population. And there's also lots of research that found out that people that suffers from those disorders express themselves online profusely. So we could use some automatic means such as NLP-based approach to support them better. But one of the caveat is we have a hard time getting enough data because machine learning requires lots of data, but it's hard to get good and valid labels because we can use clinically grounded annotations, which would be the holy grail, but it's extremely. Oh, do you still see the presentation? On my hand, the monitor is kind of working.
Yes,
okay.
We can still see it.
Okay, perfect. So clinically grounded annotations are costly and they require access to the author because, what I express online isn't like a clear, accurate representation of my mental health. So other alternatives that we can see in the literature is, when I type in my text, hey, I've been diagnosed with depression, and use that as a label, or sometimes just my affiliation, or whether or not I'm a member of, let's say, the subreddit r/depression. Instead of that, maybe we could use some crowdsourced data, which could be some kind of a compromise between clinically grounded annotations and the automatic ones, to explore how crowdsourced annotations, their value, and how we can possibly use them. We'll do some error analysis, and also if the crowdsourced annotation are more influential than the expert ones. We did that with a data set from CELP site that comprises more crowdsourced annotation, but kind of a good distribution between the two annotator types. We talked about influence, but what is it? How do we measure that? We do that with inference functions. In a nutshell, inference function, they try to answer the question, what if I had a different training data? Would my model be different? So to assess that, we will just, we'll do like a small upweighting of one data point, let's say ZI, and assess if the variation on the model are large or not. Those variation, there's mainly two ways to measure that. It's with the parameter change, but this is harder to interpret because you have a big vector, because there's lots and lots of parameters in machine learning models. Or we can use the loss gradient, which is assigned quantity, so it's easier to interpret. So if the derivative of the loss is negative, and then it means that if we upweight this data point, then the loss would be smaller, and which is a good thing because we're always minimizing the loss function. So this point will be said to be helpful. So for the experimental setting, we use Reddit posts from the subreddit r/suicide watch, and there is a 4-point grading scale. The model was Roberta, and we used the package FastIF to compute inference functions. This is a great package to accelerate the computing because inference function can be quite slow. And the most important thing in this slide is the label distribution. So we can clearly see that there's some domain shift between the label annotated by the expert and by the crowdsourced. Because if we look at the low and moderate class, clearly the distribution is quite different between the expert and the crowdsourced. And this is something that actually shows also, well, this is something that will affect the results. So this is very important to keep that in mind, because when we are looking at the model performance per label, we clearly see that for the moderate and low risk levels, the performance of the model are significantly lower than the other two labels. So yes, and also mental health attention tasks are always difficult. So it's not a surprise that the results are not like impressive in the 90%. So yeah, so let's try to answer the questions that we asked ourselves earlier. So if we're analyzing the errors, I mean, we have some dimension shift and data imbalance. So we have to consider the macro average for a better representation. So the macro average of the error rates between the two annotators are pretty similar, which is a good thing. But not all errors are created equal because when you're underestimating the risk level of your data, well, the consequences can be much graver than if you're overestimated. And sadly, the crowdsourced data is much more likely to underestimate the risk level. And the other question was about influence, whether or not crowdsourced annotation was more influential than expert annotation, especially because we had more crowdsourced annotation in our data set. On average, it's interesting to note that the harmful examples from each annotation source have a comparable influence when the examples are harmful. And so this is interesting because both of them, like there's not one annotation source that harmed the model more on average, which is a good thing because intuitively I did not expect that. And also when an example is helpful for most of the predictions of the test set, they mostly, and like by a large part, come from the crowdsourced annotation. So definitely crowdsourced annotation have value. Also, I hope that this little presentation showed you some kind of, give you a good impression of influence function, you know, because this technique is extremely underused and it's very powerful and you can get some very good insight from it, such as some work from Kuo and collaborators. They use influence function to fine tune further the model on the helpful example, and they showed that it improved their model. So this is something that we are looking to work on the future. So thank you for listening to my talk.
Thank you, Fanny. You were also right on time, and I appreciate that. And we, yes, please. I'm forgetting to clap because of this Zoom format, but thank you for everybody who's virtually clapping. We have one last talk, and I don't think I've spoken to the speaker yet. Let me just go back to my schedule. The talk is entitled Dataset Augmentation Using Back Translation to Improve Early Stage Dialogue Systems. Oh, I think we have Marc Curgo on the line. Man, that everybody's doing very well today. Marc, please take it away.
Thank you. So today I will present you joint work from National Bank and UQAM, and specifically CIAST, which is a Montreal-based research lab. Our goal today will be to improve early stage dialogue systems by augmenting the data sets that we have at the conception stage. First of all, let's just define the task real quick. We have a dialogue systems, which is a dialogue with which users interact in natural language. And the needs that users try to fill by interacting with that system are called intents. And the specific way in which they express that need are called formulation or utterances. We then have intent classification, which is the task of assigning formulation to existing intents from that knowledge base. As common as it is, we also have cold starting problem and building dialogue systems. We may have frequently asked user questions on a website maybe, and in the best case, you would have that informed by actual questions. But in that case, you would need more formulation to begin to train a dialogue system. In the best case, you would have maybe a chat-based call center, user service center, that you could extract formulations from, and then you would just have to annotate them. But this case is still quite rare in the industry. And so you would mostly have to augment your original data. And for that, you probably don't want to rely too much on experts to generate formulations, because then you might introduce bias towards your system rather than users' needs, and also maybe on the way in which users express themselves. So let's just try to find a way to use existing data, real user data, but try to make it make those systems more efficient from the start. We base our work on 2 open source dialogue systems, which are intent classification tasks. The first one is related to the banking system, and the second one is based on several domains, which we can see here. Banking 7.7 is a little bit more fine-grained, and the other ones just has subjects that are kind of all over the place. So different set of challenges, but still the same kind of goals. Our work relies on the back translation mechanism, which is the task of taking a sentence from the original language, passing it through an automated translation system to get our sentence in another language, here French, and then translate it back to the original language with the hope that this back and forth introduces some variability in the way in which this need is expressed, is worded, but that we keep the same meaning. Our experiments pipeline is as such. So we take the original data sets and we undersample them to mimic a case where data is scarce from the start. This is our baseline data set. We then use paraphrasing by using back translation to get an augmented data set, and also try a different set of filtering techniques to try to filter out sentences that are generated but of bad quality. This gives us a set of data sets that we use to train distinct intent classification systems, which we all evaluate against the same original test set. So the first set of experiments is we try to switch out the pivot languages, which is the language we pass through to do our back and forth and back translation. And we try to have a different set of language families with the hope that the more distant one language family is from English or from the original language, the more variability will probably introduce in this back and forth translation, and eventually probably lead to some differences in the end system results. And then we also try to filter out model outputs based on the translation model confidence in each predicted sample. And here we based our filtering on the percentile of model confidence, which is based on the specific model and data sets that we use. So as for the results, what we see is that data augmentation does help. It does bring about an 8 to 10% improvement on those really small data sets. So this is the case where we have 5 samples per intent. But then on the question of which private language is best, well, we could argue that German is a good candidate. It does perform really well, but some other languages are on par with that performance. So choice of language model does not lead to some really clear-cut improvement. And then we had the question of does filtering model output lead to performance increase? And we didn't find that at all. We found that actually to be detrimental to the end results. So basically what the takeaways we suggest are is, well, data augmentation, as in many cases, does improve the performance on data scarce situations, but especially back translation is a good way to generate those formulations. And we found that pre-trained models are pretty much good to use out of the box. Maybe try to use German as one of the candidates, but apparently experimenting further with that is not that necessary. Which is good news because you can use them basically in any system, any dialog system you try to kickstart, and then this will allow you to get your system into production sooner and collect those precious real user data, which is where the performance gain improvements are most likely to be useful in long term. Thank you very much. I believe my time is up.
Thank you, Marc. I feel bad about this, but given the size of our program, we're 2 minutes from the end already, even though all our speakers were on time, and I don't believe I wasted much time. So I'm just going to propose that if anybody has any questions or wants to discuss these papers with the authors, I invite everybody to go to the Gather Town if they want and have the time. I unfortunately cannot be there, but again, I'd like to thank all our speakers for being on time, and I'd just like to close this session and congratulate all the speakers on their talks. Thanks to everybody.
Thank you.
Thank you.
So I just put the link on Gazotown on the chat, and just to remind you, we have the presentation of the best doctoral thesis coming soon. So I apologize for not having, due to the compressed schedule, not having more time for questions this session, but the Gazotown is here also for the complete conference, so you can always send a private message also via Zoom to people and ask to meet on Gazotown at some other point. So yeah, just to remind you, we should start the best doctoral thesis presentation soon. So normally I am not the chair of the session, so but the chair has not arrived yet. So maybe we are just gonna wait a few minutes, and if not, I will take the lead on sharing this session. So we have the presenter, Jinsheng. So can you just check if you can share your slide, maybe just while we wait for. Okay. So maybe if you are okay to wait like 2 or 3 minutes, Jinsheng does before we start.
Sure. Do you see my shared screen now?
Yeah.
Okay, sounds good.
And we can hear you, so I think it seems to be working. Yeah, so just maybe wait like 2 or 3 minutes also, because the other session just ended. So if people want to stretch a bit their leg and just like 2 minutes, that will be.
Yeah, sure.
Sebastian?
Yeah.
In the previous session, the chair invited everybody to gather town.
Yeah.
So maybe there's some people in Gather Town. I was on Gather Town, then I realized there was a session here. It's about.
Yeah, so maybe I can go after. So technically, I think it's possible to leave a parallel live, one on Zoom and one on Gather Town, but
okay.
I agree it's not a good age. Yes. So yeah, maybe we can just wait a few minutes and I will go to Gather Town just after to announce the. So in contrast, in most of the session, we don't have the coffee buffer like we had. Yeah, so maybe just wait 2 minutes and we can start after that.
All right. Sorry for the delay. Good afternoon, everyone. My name is Richard Curry, and I am president of Kayak. And it is my privilege today to announce the winner of our award for Best Doctoral Dissertation in AI for 2022. The winner is Chi-Cheng Mei from the University of Alberta for his dissertation, Non-Uniform Analysis for Non-Convex Optimization in Machine Learning. Well, congratulations. Dr. May's dissertation has been described as a tour de force. It solves several open problems in reinforcement learning and optimization, and provides new theoretical concepts, new technical tools, for optimization and online learning. It solves problems that were considered among some of the more difficult in his field. As testament to the quality of his work, the results of his thesis were published in ICML 2020, NeurIPS 2020, ICML 2021, and NeurIPS 2021. So I think, and have received over 110 citations to this day. So as a badge of quality of work, this is absolutely amazing. So on this note, I'll give the floor to Dr. May.
Thank you, Richard, for the very kind introduction. Do you see my shared screen now?
Yes, we see it.
Okay, great. As Richard introduced, I'm gonna present my thesis work in University of Alberta, non-uniform analysis for non-convex optimization in machine learning. So I'll go through the following 3 or 4 parts. Firstly, I will talk about what do I mean by those non-uniform analysis in the title. Then I will mainly focus on the results we got in reinforcement learning by using those notion of non-uniform analysis. Then I will mention a little bit about some other progresses in supervised learning as well as in general optimization problems. So as also mentioned, this is based on a bunch of published results in ICML and NeurIPS papers over the past 2 years. And we start from something people have been widely used in practice or in analysis. And there's one thing called smoothness. When people are doing optimization, they often use this kind of tool notion to do analysis. So the smoothness is the following thing. If we look at a function, if we look at its second order derivative and look at its absolute value, and if this kind of quantity can be uniformly upper bounded by a constant beta, which is shown in the red part in these slides, then we say this function f is beta smooth. So why this is useful? Because it can be used to do analysis gradient descent or gradient ascent based algorithms. So as long as the function is beta smooth, and if we do one-step gradient descent using some learning rate, which depends on the beta quantity, then there's a descent lemma, which says after we do one gradient update, the progress, which is the current function value minus the next iteration's function value, is always guaranteed to be large enough to be larger than or equal to constant times the current gradient norm square. And there's another property I would like to mention a lot in this talk. It is called something like a gradient dominance or Loyal-Savage inequalities. It is kind of recently used to get some progresses in non-convex optimization to get a global convergence. For example, policy gradient algorithm, policy gradient optimization in reinforcement learning, and generalized linear model training in supervised learning, as well as some over-parameterized neural network training. So I will mention this property a lot, but basically it is saying the inequality here. So gradient norm will dominate suboptimality gap times some uniform constant capital C here. And the next, I'm gonna show how those properties are not satisfied by some simple examples or as well as practical examples. So consider the simple function fx equal to x24. Then if we take its second order derivative, then it is proportional to something times x squared. And the x squared will be unbounded as long as the magnitude of x is be unbounded. And x squared is gonna approach arbitrarily close to 0 as long as the magnitude of x is arbitrarily close to 0. So for something like this, it can grow unbounded or arbitrarily close to 0. It is just not possible to use a uniform quantity beta to characterize the function property over its entire domain. So another more practical example we can see in machine learning is something we call generalized linear model. So say we want to minimize some square laws between some fixed prediction, between some prediction and fixed targets. And the prediction is produced by linear feature plus some nonlinear activation like sigmoid function here. And if we visualize this function, visualize this landscape as a function of the parameters, then we can see it is highly non-convex. And it is also non-uniform in the sense that at different locations on the landscape, the function behaviors are very different, such that if we do gradient descent, there are some plateaus where the gradient is pretty small. And as a result, we can show in the right subfigure, the blue curve is the learning curve for gradient descent, and it will just get stuck for a very long time. So then those are the problems of when we are trying to use existing properties to analyze optimization problems. And the thing I did in my thesis work is basically the following modifications. So the only difference to the previous properties we just mentioned is this time beta is just replaced with beta theta, which depends on the parameter theta at different locations. And the capital C here is also replaced with capital C theta, which depends on parameters as well. Then we can do some new algorithm. Instead of using just 1 over beta as the learning rate, we can use 1 over beta theta t at iteration t. Then this algorithm, we call it geometry aware normalized gradient descent. And we will also see its performance later. So that's basically what I mean by non-uniform analysis, proposing some properties which non-uniformly depends on the parameter rather than uniformly over the entire domain of the function. Then next, I'm gonna show some progresses we have obtained, how to use those non-uniform properties to get some results in reinforcement learning, basically policy gradient optimization. So for the background, I would like to spend several minutes to introduce the notations and the settings of reinforcement learning. It is usually mathematically formulated as a Markov decision process, which consists of state action spaces, which are both finite, which means there are a finite number of states, finite number of actions. And there's a one-step reward function, which take a state action pair as an input and output a scalar. And there's also something we call transition function, which also takes in state action pair as the input and output probability distribution over the state space. And there's something we call discount factor for calculating value function. So the target concept or the key concept in reinforcement learning is something we call value functions or state value. So it is calculated by accumulating expected discounted reward. And such a thing is a result of interacting using a policy between agent and environment. At each time step, the agent is presented by a state from the environment. Then the agent would take an action based on its policy. The environment will receive the action and return back immediate reward and next state. And after a while, the agent will basically have an experience, which is a sequence of the current state the current action, and the current immediate reward, and the next state, next action, next immediate reward, and so on, such that it can accumulate the reward it has calculated, collected. So that's the thing we call value function. And there are some similar related definitions like state action value and advantage functions. And the goal is to adjust the parameters of the policy such that its long-term value function can be as large as possible or equivalently can be maximized. So we are interested in some methods we call policy gradient based. And it is a core concept of policy search and ethical critique methods in reinforcement learning. So about more than 2 decades ago, there was a basic paper talking about policy gradient theory, which is shown in the left. So it basically says the following things: as long as the relationship between the policy pi and its parameter theta is differentiable, then we can use the formula here to calculate the gradient of the value function with respect to the policy parameters. And if we have the gradient, the policy gradient thing, then we can do algorithm, do an iterative update, such that in every iteration, we calculate the value function's policy gradient with respect to the current policy's parameter and do one update to get a new parameter as well as a new policy. That's the algorithm we call the policy gradient method. So we do something which is also widely used. It is called softmax transform. And the purpose of doing this is to guarantee the output is always a probability distribution over actions under every state. Usually people learn some parameters for every class or every action, then put it into a softmax transform, which is defined by exponential normalization, such that it is exponential, then it is always non-negative. And it is normalized such that the probability sum up to 1 for across all the actions under every state. And using such a parameterization, we can just use the policy gradient theorem formula to calculate the gradient with respect to the policy parameter theta for every state action pair here. It's a product of several terms like the discount factor, state distribution, policy, and advantage function, which is Q value minus the state value. The first difficulty here is this softmax transform will make the value function maximization problem a non-concave maximization problem over the policy parameter theta. And we are still using some gradient-based method, which is basically policy gradient. So the question whether using a gradient-based method on a non-concave maximization problem will guarantee a global convergence towards the optimal policy or not is a question. So our first contribution here is to positively answer this question. The answer is yes, it will finally converge to the globally optimal policy. And it will get a stronger result. It is called 1/t convergence rate. So it is basically the inequality at the bottom. The left-hand side is smaller than or equal to the right-hand side, where the left-hand side is something we call suboptimality gap. It is defined by the difference between two terms. The first term is V star. It is the global optimal policy's value function, which is the largest possible value function over all possible valid policies, minus V pi t, which is the value function of the policy pi t produced by the policy gradient method at t's iteration. So such a thing measures a distance of how far or how close the policy pi t is to the global optimal policy. And such a thing is going to be smaller than or equal to constant over t, where t is the number of iterations the algorithm has performed, or the number of policy gradient updates the algorithm has performed. And the constant depends a lot of problem-specific things like state number, discount factor, and other quantities. So the key reason we can show policy gradient-based method achieve global convergence on a non-concave policy gradient policy optimization problem is the middle part. It's something we show the gradient dominance, such that the gradient norm is going to dominate the suboptimality gap. And here's a sketch using the same we established for smoothness, such that every time we do one gradient update, we get a progress, and the progress is proportional to constant time the current gradient norm square. Then we get the first inequality. And use the inequality we just said is called gradient dominance. Then because the gradient norm is gonna dominate suboptimality gap, so gradient norm square is gonna dominate the suboptimality gap square. And because of this, and a simple induction argument will give us a 1/t convergence rate. And next, we can actually show this kind of 1/t convergence rate is unimprovable, such that if we use just bounded learning rate, then there's lower bound of 1/t. And the reason is the policy gradient norm is not only dominating the suboptimality gap, but it is also dominated by the suboptimality gap, such that if we do one gradient update, then the progress cannot be too large. That's why there is a lower bound of 1/t. Then such a thing can be verified. We do some true gradient update on one-state MDBs where there are 20 actions and the reward is bounded. As shown in the subfigure, the third subfigure, the y-axis is the log suboptimality, and the horizontal axis is the log t, log number of iterations. And the slope is pretty close to -1, which means log suboptimality is approximately minus log t plus some other constant. Or equivalently, the suboptimality itself is constant over t, which is the number of iterations the algorithm is producing. So that's basically verifying this 1/t convergence rate things. So that sounds pretty nice because we get a global convergence rate on a non-concave maximization problem. But the practice will tell us this is not going to guarantee a good practical performance of this algorithm. And here's a simple simulation we have conducted. There's one state and there are 3 actions. And the leftmost triangle corresponds to the probability space of that 3 action problem, where the bottom left corresponds to the probability of 1, 0, 0, which means the first action is going to take probability 1. The other 2 actions are going to take probability 0. And the rightmost corresponds to 0, 1, 0, which means the second action is going to take the probability 1. The other action, 2 actions, are going to take the probability 0. Similar for the top corner. So the problem here is this algorithm is very initialization sensitive. Close to the top corner, we are going to make 2 different initializations, but they are pretty close to each other. And their learning curves are shown in the middle and the right subfigures. In the middle figure, that's something we call good initialization, where after only 100 iterations, the policy's value is pretty close to the global optimal policy's value. Where for the rightmost subfigure, it only perturbs the good initialization a little bit, but the behavior is going to be very different. The iteration is going to be firstly attracted toward suboptimal actions corner, and we'll get starts that there for more than 8,000 iterations, and finally escape that to approach global optimal policy. So that basically means this method in its nature is very initialization sensitive. And we can formalize this. There is always a valid policy such that it is far away from the global optimal policy, such that the suboptimality gap is always larger than or equal to constant, let's say 0.5. But the current policy gradient norm can be arbitrarily small, smaller than epsilon order, such that every time we do a gradient update, we can only get epsilon progress. And to get a constant progress such that the suboptimality gap 0.5 can be closed, we need to do 1 over epsilon, this number of iterations. That means the iteration will get stuck on plateaus for at least 1 over epsilon number of iterations. So such a thing can be characterized. So that's basically a gap between theory and practice. In theory, we are guaranteed to use this policy gradient algorithm to achieve a 1/t convergence rate to global optimal policy. But in practice, we observe it can experience some suboptimal plateaus as well as initialization sensitivity. And to my understanding, this is a result of the following combination of three things. Objective, we are maximizing the value function. And algorithm, we are just using gradient-based gradient ascent. And the parameterization, we are basically using softmax parameterization. And below, I will introduce how to properly modify each one of those three components to achieve better results in this setting. So the first thing I'm going to talk about is to modify change the objective. A widely used technique in reinforcement learning is something called entropy regularization, such that people, instead of maximizing the original value function, we maximize the original value function plus something called entropy, which is defined by accumulated expected negative log property of the policies. And using such a regularized optimal value function, we can show that the gradient will no longer converge to the original deterministic policy because the objective function has been changed. And it will converge to something we call regularized optimal policy. And if we look at the optimal regularized suboptimality gap, then we can show some faster convergence rate. It's no longer 1/t, it is 1/exponential t, where in the exponential, there are some other problem-dependent constant. And the reason here is there's a better relationship between the gradient dominance, between the gradient norm and the suboptimality gap. So previously, we have policy gradient norm dominating suboptimality gap. Now, for the regularized objective, we have policy gradient norm dominating square root of suboptimality gap. So whenever we have a suboptimality gap very small, for example, 0.001, then the square root of it will just be 0.1, which is one order of magnitude larger than the original value of suboptimality gap itself. That means we do one gradient update, we get a larger progress. That's why it is going to converge faster than the original unregularized policy gradient method. And it can also be verified by simulations. As before, the original policy gradient method will get stuck on a suboptimality plateau here for more than 8 million iterations. And the regularized version will pretty quickly, less than 1,000 iterations, you will escape from that plateau and achieve approach regularized optimal policy. So next, what if we don't want to change the objective? We just want to keep the original value function and to optimize it. Is there a way to still achieve better results than the original policy gradient method? The answer is yes. And the thing is also kind of widely used. That's something people call nature policy gradient or mirror descent. So instead of doing just policy gradient ascent, in nature policy gradient, we firstly calculate the gradient. Then we calculate something we call Fisher information matrix, or the pseudo inverse of it, such that we use this matrix to left multiply the gradient and do a kind of preconditioning. And after preconditioning, we do the update. And such a thing update, we can also show a faster convergence rate on the policy optimization problem. It is also 1/exponential t. And the reason is as follows. So this time, the progress is no longer policy gradient norm square. It is the inner product between policy gradient and nature policy gradient. And we also established a better relationship between this quantity and the current suboptimality gap. So it's going to be larger than every time we are going to get a constant factor of the current policy gradient, current suboptimality gap as the progress. So as a result, it will show a linear convergence rate or exponential convergence rate. And there's a second way. If we don't want it to use this kind of preconditioning nature policy gradient, we can do something else. So the thing is related to what I mentioned at the beginning, the non-uniform smoothness. And the left subfigure is what I have shown before, the plateau of the learning curves of the original policy gradient. as shown in the blue curve here. And the right side figure basically shows the second order derivative in the blue curve. And we can observe that it gets pretty close to zero whenever the iteration is on the plateau, getting stuck there. And the right curve is the gradient norm at that iteration times some other constant. And we can see that this red curve is gonna characterize our upper bound, the blue curve, in a more precise way than any other uniform constant, let's say 0.5. So such a thing can be formalized such that when we calculate the gradient, the second order gradient derivative of the value function with respect to the policy parameter, and look at that matrix max largest absolute value, then it is always going to be smaller than or equal to the current gradient of times some other constant. And as a result, we are going to use 1 over beta theta rather than 1 over uniform constant beta as the learning rate. And because of the beta theta is something times gradient norm, then 1 over beta theta is just going to be behave equivalently to normalizing the policy gradient at the current iteration. Then this will give the algorithm here, as shown in here. So such an algorithm will also converge much faster than the original policy gradient algorithm, achieving 1 over exponential t global convergence. And the reason is at each iteration, we get the progress as policy gradient norm itself rather than policy gradient norm squared. And imagine whenever the policy gradient norm is very small, for example, 0.01 or 0.001, then the policy gradient norm has to be orders of magnitude larger than the policy gradient norm squared, because that gradient norm is just pretty close to zero. Then because of this, every time we get a much larger progress, then this method will converge much faster than the original version of policy gradient method. And it can also be verified for both the faster convergence rate as well as faster escaping from the landscape plateaus. So finally, if we don't want to change objective function, and we don't even want to change the update, we don't want to do nature policy gradient or normalization things, is there still a way to achieve a better results than the original policy gradient method? The answer is still yes. And the reason is from looking at the softmax policy gradient. As shown in the first formula, it consists of product of two things. So current probability of that action times reward or value of the action. The second thing is a good thing. That means a good action will have large reward. So we want the method to put more probability on the good action with large reward. But the good thing, the first thing, which is the current probability, policy's probability on this action, is gonna discount possibly the second part. So if there's a good action with a very large reward, but its current probability is very small, say 0.01, then it's gonna be just basically 1% of the original value the reward of that action can provide. So that basically means after we do one update, the good action doesn't get much progress update on its parameter as well as its probabilities. So this is basically a result of taking derivative using the softmax transform. So as long as we use the softmax transform, such a kind of thing will appear. So the idea here is instead of using softmax, which is defined as exponential normalization, what if we use something else rather than softmax? So here we take an attempt using something else. It is called Escort transform. So instead of exponential normalization, we do some polynomial normalization. It's gonna take the parameter and take absolute value to some other exponent, then do the normalization. Then the p here, if p, for example, is 2, then we basically get a square normalization of theta. And the reason, intuition, why it can improve over the softmax policy gradient is as follows. So still look at, consider what if P is equal to 2. Then in the bottom formula, there's a raising probability to 1 minus 1 over P. If P equal to 2, then that's basically square root of the pi probability of the action. And if that action's current probability is very small, 0.01 again, then the square root of it will be 1 order of magnitude larger than the original value of this probability. So the closer the probability is to 0, the more order of magnitude this square root will be larger than the original value of the probability. That also means a larger prowess if we do every update using the new transform. And here is like more formal result of showing this new parameterization is gonna give us better results, better convergence dependence on the quantity than the original softmax parameterization. And this is like a simulation verification thing. So we start from the same initialization and using different transforms. Then the blue thing is the softmax thing. It will get stuck on some suboptimality plateaus. And those colorful curves are for using different p values, including p equal to 2, 3, or 2.5. So those curves appear to have a stronger resistance against the attraction from the suboptimal corners. They will not get stuck, they will escape very fast, much faster than the original softmax version of policy gradient. And here is basically some more simulations on more complicated environments like multi-banded with multiple actions like 2050, as well as a 4-room environment, where we can show in the blue curve the softmax policy gradient will keep getting stuck on suboptimality plateaus. And the red curve shows that the new transform will give us a better learning curve in terms of the smaller suboptimality gap. So that basically conclude the conclusions we have obtained in policy gradient optimization. For a brief summary, it's kind of like we look at the 3 different components in this problem: objective function, algorithm updates, or parameterizations. And we use entropy regularization to change the objective such that we achieve a better non-uniform loyal switching equality to achieve a better rate. And we change the algorithm from the original policy gradient to nature policy gradient or normalized policy gradient such that they use the non-uniform landscape information of this value function with respect to the policy parameter and achieve also better results. And finally, if we change the parameterization, we can still do that because inequality will contain a better initialization dependent constant. So then the next question is, all the previous conclusions hold in the true gradient settings, where in each iteration we have the excess of the policy gradient with respect to every state parameter pairs. But however, in practice, we don't have that. Every time in reinforcement learning, we can only sample one action using the current policy and do one update. And if this is the situation, we need to estimate the true gradient from samples. And the thing people are usually doing is called on-policy importance sampling. Every time we sample one action and we observe that sampled action's reward, and we construct some estimator such that it is gonna be in expectation equal to the original reward vectors. And all the 3 methods we just mentioned, for example, softmax, nature policy gradient, or normalized policy gradient, can be generalized to those stochastic settings if we replace those true mean reward vector in the true policy gradient by the reward estimators. Then we get an estimated policy gradient vector and then do an estimated update. However, the conclusions here are pretty surprising. It's gonna be reversed if we compare the conclusions to what happened in true gradient settings. In true gradient settings, we have one slow method original policy gradient, softmax parameterization. We have two strictly faster methods, natural policy gradient and normalized policy gradient. But if we generalize them naively, as we just mentioned, to the stochastic on-policy settings, then the slow method will still achieve some global convergence result. But those two faster methods in the true gradient setting will fail in a worse way, such that they will diverge, they will converge to suboptimal deterministic policy with positive probabilities. And the reason why they fail in this on-policy stochastic setting is exactly the reason why they are better method in the true gradient setting. It is because they are too aggressive. And if the method is too aggressive, then it will resolve something as follows. It will make the sampled actions probability too close to 1, such that when we calculate the infinite product of that action's probability from the finite time to infinite time, which basically means how likely we are going to sample this action forever, then this infinite product is going to be strictly positive as long as the probability is approaching 1 too fast. That means there is a chance to sample some dominating suboptimal action forever without sample any other action for even once. So that basically means that's the reason why those aggressive methods would fail in the on-policy stochastic settings. And using this kind of intuition, we actually can establish some trade-off between stochastic optimization. There's if a method is not using any oracle information like the optimal actions reward or the reward gap, is that kind of information is not revealed to the algorithm, then the algorithm can at most achieve one of the following two results. It either converges to the global optimal policy almost surely with probability 1, but its convergence rate cannot be faster than 1/t. Or it can sometimes achieve a faster than 1/t convergence rate. But the price it has to pay is it has to fail to achieve to a global optimal policy with some positive probability. That's basically a trade-off. So aggressive method will fail with positive probability. And if you wanted to guarantee almost sure convergence rate, then the method itself cannot be too aggressive. So then that concludes, really concludes our results we obtained in policy gradient optimization. So now I wanted to mention some other progresses is in supervised learning. That's something we call generalized linear model. As we have seen before, that's something we are gonna where we are gonna minimize some square loss between predictions and labels. The label is always fixed. Then the prediction is produced by linear feature, then some nonlinear sigmoid transform, such that the output is always a probability, a value between 0 and 1. So such a objective, if we use nonlinear transform like sigmoid, is well known to be non-convex, not even quasi-convex. But the result people already got is if we use some normalized gradient, then it will converge to global optimal solution at 1/t rate. That's the best known result before. So now we have a much stronger result. It is 1/exponential t if we do some other updates rather than 1/t. So the thing here is left-hand side, we still run the gradient descent. Then we look at the learning curve. Then there's a similar plateau thing as we have seen in the policy gradient optimization, such that on the plateau, the objective value doesn't change much. That basically means the gradient update almost stay at the same place because of the small gradient. And on the right-hand side, that's also similar things. The blue curve is every iteration we evaluate the function's absolute second-order derivative. That's the thing we call a smoothness coefficient. And the red curve is the formula here. is the sum of the gradient norm plus some other ratio. And within that ratio is gradient norm squared times over the objective function value itself. Such a thing is gonna characterize the blue curve much more precisely than whatever other uniform constant, for example, 1 or 2 or 1.5, whatever. And we can use this beta theta to do update. Then the result is basically as follows. In the middle figure, if we just use normalized gradient with constant learning rate, then it will not converge, because if we normalize the gradient norm, then the gradient norm is going to be smaller and smaller, because the gradient descent is going to approach some stationary value, which has almost 0 gradient norms. That basically means the update itself will be larger and larger if we just use constant learning rate. Then it will start oscillating forever. That's the blue curve. And the red curve, if we take into account that beta theta coefficient and use that as a normalization rather than the gradient norm itself, then it is going to achieve a better, faster convergence rate. So that basically is the generalized linear model results we have obtained. The next, I would like to also introduce, present another results we obtained in supervised learning. It is as follows. So say we are using some cross entropy loss, which is also widely used in, say, classification problems. And as long as the true mean label or true the target distribution is one hot, which means there's one class over several class, it's gonna take probability 1. That means this data set is always deterministically belonging to one class, and all the other class likelihood will be exactly 0. Then in this case, we can observe something we call softmax damping. So it is basically saying the convergence speed will be slower and slower as long as the prediction is closer and closer to the one hot distribution. And that's basically is from the reasons that if we look at this gradient, such a gradient characterizes how much progress we can get from doing one update. And left-hand side is just the gradient norm square. The right-hand side is objective function value times some quantity. And that quantity is a problem. That quantity is basically the minimum probability over all the classes for this classification problem, let's say. Then as long as the probability, the prediction is closer and closer to the one hot true label target distribution, the minimum probability across all the classes is also approaching 0. That means we do one update, we will get smaller and smaller, closer to 0 progress if we keep doing gradient descent. So that's the reason why it's gonna getting, the progress is gonna getting smaller and the convergence is getting slower. So, and also use something we mentioned before, those kind of polynomial normalization transform. For example, p equal to 2. Then the red part, we can see that as long as p equal to 2, then the exponent will be 1 minus 2 over p, which becomes 0. That basically means there will be no longer dependence on the minimum probability across all the classes. So that means if we use this new transform to do cross entropy minimization for classification, as long as so as the policy, as the likelihood predicted is approaching the true one hot target distribution, the progress will no longer become smaller and smaller because the red part will always be 1 here. So, and as a result, we'll get a true 1 over exponential convergence rate in this setting, as shown in the theorem here. And that can be, okay, so then finally, I would like to talk a little bit about general optimization. So the previous 2 things or 3 things we have talked about is policy gradient optimization, generalized linear model training, and cross entropy loss minimization. So such a result actually analysis can go beyond those scenarios to general optimization problems. So say here, we wanted to minimize some function. Let's say the function is pretty simple, defined by x to x absolute value to 1.5. Then using the standard gradient will give us a learning curve as shown in the rightmost blue curve. It will firstly approach the global optimal solution. Then it will get back. I mean, the object value will become larger again. Then it will get away from the global optimal solution. The reason here is basically, as shown in the middle figure, is second order derivative absolute value is becoming larger and larger whenever the parameter is getting closer and closer to 0. So that will make the function very steep, especially when x is pretty close to 0. So if we do gradient descent using constant learning rate, it will basically say current x is positive. Then the step will be large enough such that after one step gradient, it will hit another side, which is negative x of the function. And the function value will become even larger than the previous iteration. So then next iteration, similar things will happen. So it will basically happen again and again. And in the learning curve, it will look like it will start oscillating forever. So that's basically something we didn't mention before. And it is some other minimization problem rather than policy gradient minimization and generalized linear model training. But it basically shows the thing that such a thing, if we calculate beta theta and use it as a normalization factor to do the update, we can achieve better method than standard gradient descent on this object. So that's basically is one example of how we make it more general to general optimization problem. That basically concludes my contributions or result we have obtained in my thesis work. And now we are also actively working on some future directions. So the very first thing we are gonna study is to design some better method for stochastic policy optimization. Because I just mentioned that the faster method in true gradient settings will fail in a worse way in stochastic settings. So how to make those faster methods still work in stochastic settings, that's a problem we are currently looking at. And another problem I'm considering is those kind of things can be used to characterize the landscapes of neural networks. From literature or existing works, we know that if a neural network layer is larger than 3, then there has to be some degenerate settle points. And around those degenerate settle points, the plateau will appear again, which means the landscape will be very flat. So that will create a similar problem as we have seen in policy gradient optimization, the initialization sensitivity and suboptimal plateaus. And studying that would be also another interesting question. So then later, next we are gonna consider some more complicated or practical settings for both policy gradient optimization as well as other optimization problems, because we consider softmax tabular representation where each state action pair will have a scalar parameter. And what if we don't have a scalar parameter for each state action pair? What if the parameterization is some low dimensional feature and parameter? Then that's the thing we can investigate. So finally, we are also considering some other, using those results in some other settings, because I just mentioned single agent Markov decision processes. And in some other more complicated settings like multi-agent game theory and potential games, those problems can be more complicated than what we have seen in single agent settings. So that's basically my presentation. Thank you for your attention. And if there are any questions, I'd be happy to take it. Yeah, thank you.
Thank you, Dr. May. That was a very interesting talk. I can see our committee really picked a very strong doctorate for the prize this year. Congratulations again. We'll open the floor to questions. Who would like to go first? I'd love to ask some questions myself. Optimization is not actually my area of expertise. So your thesis is a bit out of my depth. I'm well, pleased to say, since you've won the best thesis, obviously. So someone?
Okay, we have one question from the in-person audience here.
We have to ask some question. Just on your result, where are we? Okay, where's the camera? All right. We're here in person. This is Mark Crowley from University of Waterloo. Great talk. I have to go process some of your papers and reading to get it. But you had some results there. I think your contribution 3 or 4 about bounds on the reinforcement learning convergence, and was 1 over epsilon. I missed as you're going through. But was the epsilon? What's the scale of that? Like practically, how does that affect things?
Oh, I see. I suppose. Sure. So the epsilon, if I remember correctly, is the gradient norm magnitude. So that basically means there are some policies such that the policy itself is far away from optimal policy. But the policy gradient norm's magnitude can be very small, can be epsilon scale. And if that's the situation, and if we start from there and do the policy gradient method update, then we will spend at least 1 over epsilon number of iterations to escape from that plateau, to get any constant progress compared to the suboptimality gap. Yeah.
Okay, so that could be that's the kind of cost to get out of every local minima in a sense.
Right, that's basically the amount of time the method is gonna spend at bad places. Yeah.
Okay, great. Thanks.
Yeah, thanks.
Any other questions? All right. In that case, and we've actually just gone a few minutes over time, but that was well worth it. Actually, we started late, so your talk was perfect, Dr. May. So congratulations again on your award and your doctoral dissertation. I'm confident you have a brilliant career as a researcher or professor ahead of you. And that concludes then our sessions for Canadian AI for today. I'll see everyone tomorrow morning.
Thank you so much.